Hi everyone, hope you all are doing well. So today we are going to discuss SSB in 5G. So if we talk about LTE, right? So in LTE we have seen, right, initial synchronization happens with PSS and SSS. But if we compare it in 5G, so there comes the concept of SS block, and SS block means synchronization signal block, right? So I'll be going slowly. For the beginners so that beginners can also understand this, who are pretty much new to 5G. So SSB is your basically synchronization signal block. Okay. So in LT, this SS block was consist of, this PSS plus SSS. This was in 4G. But if we talk about 5G, right? So it consists of your PSS plus SSS plus PBCH. And why do we use SSB in 5G? Basically, for your initial synchronization purpose. Initial synchronization purpose. So in case if you want, you can switch to 1.5, on the YouTube. So I'll be going slowly here. So now, PSS and SS and 5G NR, basically, if we talk about the functionality, right, similar to LT, it used to decode the PCI. PCI physical cell ID. So in LT, we were having the formula of 3 into secondary cell group plus PSS, right? So if we talk about NR, so in NR, what is there? We have, let me scroll it down. So in NR, we have basically 1008 different cell IDs. Okay, how many? 1008 PCIs. So now comes SSS. SSS ranges from 0 to 335, and PSS ranges 0, 1, comma 2 like LT. So if we have this formula and calculate, so it comes around 1008 total number of total PCIs. Now, if you understand why PCI is necessary, so PCI is necessary for cell search procedure, right? So that we can identify which cell we are camping on, right? So in cell search procedure, what happens? This procedure allows UE to acquire time and frequency synchronization, right, with the cell and detect the PCI of that cell, right? So during cell search operation, this time and frequency synchronization can happen in multiple ways, right? So let me change this. Okay. So it can happen in multiple ways. So what are the different scenarios in which cell search procedure can happen? So the very first one is when the UE is powered on, right? When you turn on the UE, what happens? It looks for the cell. Second is mobility, basically. So mobility happens in connected mode, right? Connected mode. Third one is your idle mode mobility. What is idle mode mobility? Basically your reselection. Okay. Next one is your inter-rate mobility. So these are some scenarios where, UE uses an NR synchronization signal and PBCS to derive the necessary information required to access the cell, right? And one other aspect of synchronization signal is that this can also be used by our UE to basically, measurement of your RSRP and RSRQ. Okay. So going further, in LT, what used to happen? So if I talk about 4G, right? What used to happen? PSS, SSS, and PBCH. Those were fixed in time and frequency domain, right? But in 5G NR, what happens? We have different subcarrier spacing, right? So like we have this mu, right? Numerology indicator. So it values like 0, 1, comma 2, comma 3, 4. And 2 to the power mu, this depends the numerology. So 2 to the power 0 means into 15 kilohertz. So we have different subcarrier spacing, 15 kilohertz, 30, right? 60, 120, and 240 kilohertz. So 15 and 30 you use for FR1, right? FR1 is your frequency band, okay? And 60, 120, 240 you use for FR2, right? So this one is the major differentiator here, okay? Uh, so if we talk about our 5G and R, right? So both are uh, PSS and SSS, right? So both the things uses BPSK modulation, right? So this would be using your BPSK modulation. So we were talking about PSS and SSS in NR, right? So PSS and SSS in NR uses BPSK modulation scheme, right? So PSS is using BPSK modulation with your M sequence. So this is your, sorry. So this is your M sequence, right? And SSS is using the gold sequence. So this you can read out more on Google. So this is not much, we are not going into much into details for this one. So this is M gold sequence with the generator end length of 127. So total active subcarriers for, if we talk about SSB are 240 subcarriers in the frequency domain and 4 OFDM symbol in time domain. Okay. So moving forward, basically, first question comes, what is the purpose of SSB, right? The very first instant I have told you, it is used basically for carrying specific signals for establishing downlink synchronization. Okay. So position of SSB in frequency and in frequency domain basically cannot be the center frequency which used to happen in 4G. Why? The simple thing is we have the concept of BWP in the 5G where we have different, bandwidth parts across your frequency, frequency band. So you cannot have it in the single, at center frequency. So because this bandwidth is not fixed, you can have multiple bandwidth parts in 5G. So according to that, SSB would be, the position of SSB would be vary in the frequency and the time domain, right? So going forward, the periodicity of SSB, if we talk about, right, the periodicity could be your 5 millisecond or 10 millisecond or 20, 40, 80, 160. But most commonly used is your 20. Okay. So maximum number of consecutive SSBs, there is also a limit as per your what is your frequency band, or let's say what is your frequency range. So if we talk about FR1, so you can have, it could be your 4 or 8, right? And if we talk about FR2, it has to be 64 SSBs, right? SSBs are nothing but your beams, right? So let's say there is a base station, right? So what it would be doing, it would be doing beam sweeping, or if say beam forming, right? So like this. So this is how, I mean, the diagram is not that good. So but you understand the crux here. It is going to beam form in certain directions, right? So it could be north direction, or it could be south direction, west direction, east direction, northeast direction. So it would be beam forming, and these are nothing but your SSBs. And SSBs carry your PSS plus SSS plus PBCH, which is your 4 symbol long in the time duration, 240 subcarriers long in the frequency domain duration, right? So if we talk about 240 subcarriers, right? Your 12 subcarriers in the frequency domain consist of 1 RB, right? So how many 240 subcarriers would become the RBs? 20 RBs, right? We're going to see the structure just in some time. So main purpose of consecutive SSB is basically beam management, transmitting each SSB in a different beam, right? And RRC parameters for the SSB, this is also we are going to see, but we'll see that in basically in log analysis part. So I'll tell you what are those RRC parameters. So your RRC parameters are, the very first one is, let me take some good ink. Okay. So the very first one is your SSB position in burst. Position in burst. And second part is SSB periodicity serving cell, right? So let's go to the diagram part also. So one more thing here, right? So somewhere on the some of the websites you might see that SSB, SSB block contains PSS plus SSS plus PBCH plus DMRS type A symbol, right? So DMRS type A position. So this DMRS type A position is the part of MIP that is a part of your PBCH. Okay, so if you see here, this is your MIP. So it is similar to LT only. So if you see this blue mark, right, DMRS type A position. So this is also the part of MIP that I have told you, right? And rest things are similar to LT. So we'll go into detail of maybe later on, when, because today's concern is our SSB only. So we'll focus on SSB today. So we talked about your FR1 and FR2, right? So as per the 3GPP specifications, FR1, FR2 are the frequency ranges. So FR1 frequency range is from 450 megahertz to 7.125 gigahertz. Previously, it was 6 gigahertz, but later on, 3GPP has revised it, and now it is 7.125 gigahertz. So somewhere the websites you might hear sub 6 also, right? So it has been revised, and maximum channel bandwidth is 100 megahertz. In LT, if you remember, uh, you just paste in the comments like what was the maximum bandwidth in LT. The question for you. The FR2 is your nothing but your millimeter waves, and this FR2 range is basically from 24.25 to 52.6 gigahertz, right? Do we have pointer option? Okay, I'll do with this only. So this is the 24.25 to 52.6 gigahertz. This is having this maximum channel bandwidth of 400 megahertz. See, the channel bandwidth is very important here because it would be going to determine how many number of RBs you have as per the subcarrier spacing, right? And the third part is above 52.6 gigahertz to 114, that is under study currently, right? So I'll show you like what all bands are there in the FR1 band basically. And we have this CGP specifications with us 38.100. Let me open this. So 3GP, these are basically standard documentation which you can always refer for any verification of your test scenario which you are going to test in the 5G, right? Or any test scenario where you want to test the negative or boundary test scenario, right? You can verify it with the 3G specification whether it is allowed or not. So I'll go to operating bands. Okay, so let me zoom it for you. So this is the 5.2 section, and this is 38.101 3GP specifications, version 17.5, release 17. So if you see here, NR operating bands in FR1, right? So I'll scroll it to down. So these all are your FR1 bands from N1 to N102, right? If you see here. So some of them are FDD, some of them are TDD, right? So the FDD band here comes from the N1 to N28. Okay, N1 to N28 are your FDD bands, and your N30 to N102 are your TDD bands. Some of them are SDL also, supplementary downlink bands and supplementary uplink bands. So most commonly used FDD bands, like which nowadays people use for the testing, right? This is your N1, N2, N3, N5, right? Or N28. And in TDD, common bands are N41. This is N41, 2496 megahertz to 2690 megahertz. This is its frequency range basically. This is, I guess, this is for uplink, and second one is for downlink, right? And other bands are your N78 and N79. So 78 is 3300, 38. This is your uplink, and 33. Okay, both involves uplink and downlink. So this is same only. And your N79, so 4400 to 5000 megahertz. So the difference, if you calculate, this is going to be somewhere 600 megahertz. Yes. So this limits its uplink and downlink bandwidth. So going back to our explanation part. So, and some of the FR2 bands are, so in 5G we have these four FR2 bands defined, and 257, 258, 260 and 261, right? So these are having uplink and downlink bandwidth, and this duplex mode is TDD only for all of these four bands. So once you perform some scenario like, this, once you're latching onto FR1 cell, FR2 cell, so you can see how this difference comes into that. But let's come back to our main topic, that is that is SSB basically. So I was telling you, SSB contains PSS, PBCH, and your SSS, right? So this picture basically shows you how this distribution is happening. Let me pull it completely if I can. Okay, now I guess this is visible properly. Yeah. So if you see here, it is in the time domain. If we look down, so OFDM symbol numbers 0, 1, 2, and 3, right? And in frequency domain, this is your 240 subcarriers, 20 RBs, right? So this initially the very first OFDM symbol is your PSS, that is across 127 subcarriers. Then you have PBCS, that is across 240 subcarriers. Then you have SSS, that is also across 127 subcarriers. Then you have some guard band up there and down there. If you see, there is some difference in the upside and downwards guard band. So because of different subcarriers, and then you have PBCH for the rest of the RBs or subcarriers. And lastly, you have this PBCH again for basically your 240 subcarriers. So if you see here, PSS, SSS, and PBCH are always together in consecutive OFDM symbols, right? Each SSB is occupying 4 OFDM symbols in the time domain and spread over 240 subcarriers. It means 20 RBs in the frequency domain. PSS occupies the very first symbol and span over 127 subcarriers. And if you see, there are some subcarriers. Basically, there are 8 unused subcarriers below and 9 unused subcarriers above. So if you do the calculation, right? So let's go to the board. So PSS is having 127 subcarriers, right? And we have above 9 subcarriers unused, and down we have 8 subcarriers. So how much it becomes? 9, 8 is 17, 17. So this is 144. So 144 subcarriers. 144 subcarriers means 12 subcarrier means 1 RB. So 12 into 12, 44, 144. So it means it consists of 12 RBs, right? So the same thing is shown here also. If you see, right, 144 subcarriers, 12 RBs, your PSS and your above the guard band, you can say, of subcarriers. And rest 192 to 239, this is your 48 subcarriers. You can subtract it. And this is coming to 48 by 12 is 4 RBs. Next, if you, so this is your PVCH part above your SSS. And downwards also, these are 48 subcarriers, 4 RBs. So total RBs are 12 plus 4 plus 4, 20 RBs, right? Now, there comes an interview question from this SSB, right? So first question is, where does this PBCH comes? Where all do we have PBCH? At the, if we normally talk second symbol, third symbol, fourth. I'm counting from 1, 2, 3, 4, right? Just to calculate. So first, two, third, three, four. So second, third, and fourth, right? So second and fourth are having 240 subcarriers, right? And third one is having some of the subcarriers, 48 plus 48. So let's calculate this. So we are calculating our PBCH. So let me change to that. Okay. So we have two bigger ones, that is 240 plus 240 plus smaller ones 48 plus 48. So if you're gonna add up, so this comes as in 576, right? So this is your 576. And if we talk about the PBCH payload, right? So this 576 subcarriers. Now, if we talk about PBCH payload, so PBCH payload equals to total PBCH minus PBCH DMRS. So if we talk about PBCH DMRS, so your PBCH DMRS is your part of MIB basically. So DMRS occupies 144 REs, right? So this 576 subcarriers, I can also like say 576 REs, right? Because only one orbiting symbol was there, right? So PBCH payload would be your 576 minus 144. So it comes as in 432 REs, right? This is your interview question. What is your PBCH payload? So you can remember it 432 REs, and but you should know how to calculate this thing. Just don't become robot, okay? So coming towards the next part, now we talk about the major difference between, this your LT and 5G basically in terms of SSS. So the major difference between LT SSPBCH and NR SSH lies in the periodicity of each channel, right? So if you see this diagram, this is basically represents the LT diagram. Time domain, position period, and frequency domain position is fixed in any case. In LT, SS block, that is PSS and SSS, are transmitted in every 5 millisecond, and PBCH is transmitted in every 10 millisecond, right? So if you see here, this is the periodicity of SS, and PBCH are different in LT. However, in NR, these are same. SS block plus PBCH both are transmitted at the same time, which means their periodicity is also same. Typical periodicity of SSB in NR is 20 millisecond. By default, in general, that is being used, right? So if you see here, the red mark, this is for sync signal, PSS and SSS. The green is for your PBCH. The very first diagram is your LT diagram, and second one is your NR diagram. So in LT, if you see SS plus PBCH, both are coming together, right? So this 10 millisecond, this PSS and SSS should be repeated twice because of 5 millisecond periodicity, and PBCH, the green one, would come only at once only, right? So this is how it is representing LT. And in NR, all are together. And in 10 millisecond frame, if you see, all are coming together at certain frequencies, right? So, sorry, certain occurrences. And if we have 20 millisecond of periodicity, it means it will occur once in the 20 millisecond, if you can see here, right? So this is pretty much clear from here. Let me know if you have any questions till now in the comment section. So time domain transmission pattern of SS block in NR is different from LT-SS block. Actually, LT has only one pattern of SSB transmission in time domain. In LT, subframe number and the OFDM symbol number within the subframe is always same in any case. In NR, there are many different cases of time domain pattern of SSB transmission as illustrated below. So if you see the diagram, as per the subcarrier spacing, we have different number of SSBs, okay, and the FR1 and FR2, as I told you earlier. So if you see this typical diagram, the periodicity again same, it's 20 millisecond. I'm just talking about the number of SSBs that we can transmit, right? So the very first case here is, let me draw. So this is your very first case. So this is saying case A, F is less than 3 gigahertz. 3 gigahertz is, right, pretty much less, and SCSVR subcarrier spacing is 15 kilohertz. So you can have 4 SSBs here, right? So these are 4 SSBs. Now, if it is 3 to 6, right? So SCS is 15 kilohertz, you can have 8 SSBs. Now, NRSSB is transmitted in various different patterns depending on the subcarrier spacing and the frequency range and some other parameters, right? Now we talk about case B. Now we talk about case B, and we have this frequency is, first one is your less than 3 gigahertz, and second one is greater than 3 but less than 6, and SCS is 30 kilohertz. So if you see here, this is 4 and this is 8. The number is same, but if you see, this is going to be shrinked in the time domain. Why? Because we have increased the subcarrier spacing. So if you increase the subcarrier spacing, it will decrease in the time domain, right? The duration will decrease in the time domain. So, and this also relates to, this, if we increase the subcarrier spacing, so how our frame is going to be fixed, but your how the slot counts varies, in the time duration, how is it is going to be reduced every time you increase the subcarrier spacing. So coming towards the last case, that is our FR2 case, right? So this is your case D. So case D is basically your greater than 6 gigahertz, or you can say F greater than, as per the repeated scenario. This is, this is not updated one. So 7.125 gigahertz, or SCS is 120 kilohertz. So in 120, so I told you, right, for FR2, it is the 64 should be there, right? So you can count here, right? 8, 8, 1, 2, 3, 4, 5, 6, 7, 8. So 8 and 8. So this is going to be 32, and each one is containing 2. So coming as in 64, right? So if you see here, right, 2, 2, 2, 2. So these are kind of bundled together because this is having very high SCS. So this is shown as in, very closely coupled together basically, right? And we have KC, that is SCS is 240 kilohertz. Again, the number of SSBs would be 64 only, but again, those would be again tightly coupled in the time domain basically, right? So now let's say you have these, you understood, like for FR1, we have 4 and 8 SSBs, for FR2, 64 SSBs, but it is understand it not necessary for the E node B to send all the SSBs. It can send, this, like let's say maximum possible SSBs are 4, so it can send 2 also, 3 also, 1 also. Or like for 64, we only require 32 SSBs. So why to waste power for that, right? So within a 5 millisecond half frame, the starting OFDM symbol, just try to understand, this is very important part. Recording is going on, right? Yeah. So within the 5 millisecond half frame, the starting OFDM symbol index of a candidate SSB within SS bus depends upon the subcarrier spacing. Now, what we are going to calculate here is what would be the very first symbol of the symbol in the first half frame of SS block. And that basically depends on the subcarrier spacing. So if you see this table, right, so left on the leftwards, we have this SCS 50, 15, 30, 30, 120, 240, right? And we have this second, this column is for OFDM starting symbol. The formula we have curly braces 2 comma 8 plus 14 into n. I'll tell you how everything is working. And for the 30th case, we have this. Okay. So the very first case is your case A. Then case B, you have different formula, 30 kilohertz, 4, 8, 16, 20 curly braces, 28 into n. And case 30, 2 comma 8, 14 and case D 120, that is 4, 8, 16, 20, 28 and right. Third column is basically your sub 6, or you can say again this pretty much into FR1 only. So FC carrier frequency is less than 3 gigahertz. So as we know, like for less than 3 gigahertz, we have Lmax, number of maximum possible SSBs are 4. So here n possible values of n are 0, 1, right? If we put 0 here, we get 2 and 8. If we put 1 here, right? So we get 2 comma 8 plus 14 means 16 and 22 if you add up, right? It's very simple. Let me show you. So 2 comma 8 plus 14 into 1. Okay. So 2 comma 8 plus 14. So if you add 2 plus 14, this is 16. This is 8 plus 14, this is 22, right? This is how it is working. If you put 0 here, this becomes 0, and 2 and 8 are the only possibilities. Now, if we talk about this 3 to 6 carrier frequency, that is Lmax is basically your maximum number of possible SSBs are 8. So we have possible values of n here are 0, 1, 2, 3. If you put 0, right, so you get 2 comma 8. If you put 1, you get 16, 22. If you put 2 here, so this becomes 28, and this add up, so it becomes 30, and 28 plus 8, 36. And if you put 3 here, 14 into 3 is 42. So 42 you add in 2 comma 8. So this is 44, and your 42 plus 8, 50, right? And we don't have the, this 15 kilohertz of carrier spacing in the greater than 6 gigahertz. So it is not applicable here. This is cross. Again, case be the same scenario, 4, 8, 16, 20, 28 n, right? And possible value is for 4 max SSBs is 0. So this is 4, 8, 16, 20, 4 SSBs. 0, comma 1 if you put 4, 8, 16, 20, 32, 36, 44, 48. So these are the starting symbols that I'm telling you. This is NA again. Again, this is 30. So KC is your 30 kilohertz again. So this is, I guess it discussed the same scenario. So this is, I know this is not same. I guess this is basically telling us for the paired and unpaired spectrum. So for paired spectrum, 3 gigahertz is used. For unpaired spectrum, 2.4 gigahertz used. So that's why it is given the two scenarios. So again, the calculation is same. This is not applicable because this doesn't have 8 SSBs. So for 120 and 240 kilohertz, only scenario possible is yours this maximum number of SSBs. So again, this Lmax could be your, this 64 basically. So 64. So and accordingly, these value possible are 0, 1, 2, 3, 5, 6, 7, 8, and these are as per the specifications. And accordingly, you can have these starting symbol number in the first half frame according to your subcarrier spacing and the FR1 and FR2 that you are using here, right? So going forward, so now we are taking an example, the timing of candidate SB within the SS burst. So let's say this is the case is for 15 kilohertz. 15 kilohertz means in 10 milliseconds of frame, you have each subframe, 10 millisecond frame is having 10 subframes, and each subframe is having 1 slot. So 10 slots are there. So as we know that SS block contains, this 4 OFDM symbols, right? So this is this showing the frequency between 3 to 6, basically FR1, and maximum number of SSBs possible are 8, SCS 15. SSB starting symbols as per the formula that we saw above, right? So this is the formula, this 2 comma 8 plus 49. So 2, 8, 16, 22, 30, 36, 44, 50. That's what it is showing here. And these are the starting symbols in the 5 millisecond frame. So 2, 8, 16, 22, 30, 36, 44, 50, right? So these 8 SSBs are possible. As I have told you, it is not necessary for the E node B to send all the SSBs. And default periodicity, as you see here, is 20 millisecond. SS burst periodicity, only once it would occur. Like it could be the could be 8 or 6, 7, 4, 5 as per the E node B implementation, right? And here we are determining only the starting OFDM symbols, right? So if we talk about 5 slots, So in 5 slots, if we calculate, right? So let me take the pen. So one frame is having 10 subframes. 10 subframe is having 10 slots for 15 kilohertz, right? And each slot is having 14 symbols. So it means total symbols are 140, right? So I hope you won't be having a doubt here. So this 15, where is this going, right? It comes under pretty much into your 5 milliseconds. 5 millisecond means 5 slots to till 70. So till 70 we are having this, right? Okay, so let's go forward. So now we come to the our log analysis part, right? For the SSB transmission pattern. Basically, this is nothing but your SSB bitmap. And SSB bitmap would be telling you how many SSBs are being transmitted. Now you know that for this frequency range, this is the possible number of our SSBs. And in that SSBs, from the log point of view, in the NSA and SS scenario, you will get to know how many SSBs are transmitted. So as I told you, it is not required to transmit all the SSBs depending on the network requirement. It can selectively transmit only a few SSB and inform UE of which SSB are transmitted and which are not transmitted. This transmission pattern is informed via RRC IE information element called SSB position in burst. Remember in the very first, in the beginning of the video, we discussed SSB position in burst, right? So the very first case is for standalone SA case. This is the message of this is a part of SIB1 message. This comes under serving cell config common SIB, right? And we have two IEs information elements. The first one is in one group and second one is group presence, right? So in one group is having bit string size of 8 and group presence is having bit size of 8. Now your question might come how it is showing 64. So this in one group, so this answer is below here. So in FR1, in one group can specify all the possible SSB bitmaps, right? So, but in FR2, in one group only cannot specify all the possible SSBs bitmap because FR2 SSBs bitmap is 64 bits. But in one group can specify only 8 bits because size is 8. Now the group presence I is to handle this kind of situation. The 64 bitmap is grouped into 8 groups which comprise of 8 bits, right? So the 8 into 8 comes as in 64. Each of the group bitmap is specified by the group presence, the second IE. Combine these two IEs in one group and group presence can specify 64 bitmap, that is nothing but your 64 SSBs. You can remember this part. This is very, very important as for the interview aspect also, and this is for standalone purpose. Now in NSA, we have slightly different configuration. Now my question to you is, why do we have different configuration for standalone and non-standalone? We could have been defined the same thing like in one group presence here also. Let's say in NSA we are having short bitmap, medium bitmap, mid bitmap, long bitmap. So which could be here also, but we are dealing it differently, right? So what could be the reason? So if you have the answer, you can paste in the comment, right? We can discuss that. So in the NSA, we have these three things. And one more thing we had in this serving cell config common SIB is SSB periodicity serving cell. So this is configurable parameter in the node B configuration. So whoever is working on the network side might be knowing we have some configuration files on the base station, right? So that base station, on that base station configuration files or profiles, you can edit or you can change this SSB periodicity of the serving cell. In non-standalone, we have the short, medium, and long bitmap. So short bitmap is having size of 4-bit string. Medium is 4 and long bitmap is 64. And again, SSB periodicity serving cell is the common. The first bit, the leftmost bit indicates the first SSB, and the second bit, the second from the leftmost bit indicates the second SSB. So now you know for FR1, 4 and 8 are possible, right? So this short and medium bitmap could represent the FR1 and long bitmap would be representing FR2. So let's take the example here, right? So the very first example here, let me change this color. Right, okay. So the very first example is your one short bitmap is 1111. So it is representing your 4 SSBs. Okay. So 4 SSBs, all are 1. It means all are transmitted, right? And this is your 1, 2, 3, 4, right? In the example 2, the short bitmap is 1010. So 1, 2, 3, 4. So 1 and 3 are 1. It means 1, 3. These two SSBs are transmitted. Example 3 is medium bitmap, that is for 8. So this is basically for less than 3 gigahertz. And this one is basically for 3 to FC is 6 gigahertz, or you can also assume 7.125 gigahertz. So these are 8 SSBs. So 1, 2, 3, 4, 5, 6, 7, 8. All are 1. It means all are transmitted, right? And then we have this example 4. Let me delete these first. Okay, we scroll a little down for this. Okay, so our example 3 basically is having 8 SSBs. So all our ones means all 8 SSBs are transmitted. And in example 4, we have 1, 2, 0, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So 1, 3, and 5, 7 bits are 1. So it means 4 SSBs transmitted. Example 5 is medium bitmap again. So 1, 2, 3, 4, 4 SSBs transmitted out of 8 SSBs, right? And this is for your, as I told you, this is for 8 gigahertz. Sorry, this is your 3 to 6 or 7.125 gigahertz. Coming towards the, so if you see the next example, that is of long bitmap, again, that comes under your FR2, right? So this is showing your 64 SSBs, and this is also showing 64 SSB. So here the first, example 6, we have all bits are 1. It means all the 64 SSBs are transmitted from G node B. So, and this is example 7, where you can see starting 8 bits are 1. It means out of 64, you have only 8 SSBs are transmitted. So, and next is basically the beam detection by the UE. So once this, so once your, SSBs are transmitted, so how this works? So if you see, this is your GNB. So from the GNB, we have these two UEs, UE1 and UE2. And in above, we can see this is for NR, and we are having 20 millisecond periodicity here for SSB. So it means every two, uh, 2 frames, we are having one SSB. Let's talk about this SSB here. So which is like, we are having this 8 SSBs here, 1, 2, 3, 4, 5, 6, 7, 8. And so 8 SSBs are ranges from the 3FP to 6, or you can again say 7.125 gigahertz. So there are two UEs. So UE1 is having at the left edge and UE2 is at the right edge. So these SSBs, you can see the very, so for the first UE, signal strength for this beam would be good, right? This one. And for UE2, this beam would be good, right? So this is how precisely we can, beams could be sent or transmitted to the UE in the 5G NR. And this could be pretty much beneficial against the 4G, where specifically for the solid scenarios, where it will be having very less RSRP or SRQ. But in this case, you can particularly confine your beam toward the particular location where your user is situated. And this specifically comes in handy when the throughput requirement is high. So here are few pointers. So multiple SSBs are being transmitted at a certain interval, right? And each SSB can be identified by a unique number called SSB index. So like 8 SSBs are there, so you can say SSB 0 to SSB 7. Each SSB is transmitted via a specific beam radiated in a certain directions, right? Discussing third point, multiple UVs are located at various places as G and B. So these are two UV example. UV measures the signal strength of each SSB detected for a certain period in a period of one SSB set. Now you can understand UV would be looking in every 20 millisecond time. If the default periodicity has been configured for the 20 millisecond, and gonna detect the SSB, which is having the highest ISRP, right? From the measurement result, the UE can identify the SSB index, right? So if you talk about 0, 1, 2, 3, 4, 5, 6, 7, right? For the for UE1, this is SSB index 1 is there. For UE2, this 7th SSB index is there, which is having high RSRP. The SSB with the strongest signal strength is the best beam for the UE1. For example, beam 1 is the best beam for the UE1 and beam 7 is the best beam for UE2. So this is all from my side in the SSB part. Okay, rest we can discuss in our next video, and you can give me you can also request for the videos if you want on any topic in the 5G. I'll try to make it, and hope you will understand this video. Please let me know in the comment section, and we'll discuss more on this. Okay, thank you so much.